Dr. Sharma, namaskar.
Namaskar ji, namaskar. We can start sharp at 4:30.
Okay, so should I try? Let me share my slides then so that we are ready. No?
You can share the slides from there. Your voice is audible, it is clear. So it's like this. I will introduce you for 2 minutes, then you will speak for 40 minutes, then we can have a question answer session of 15 minutes like that.
Is my slide visible?
Yes, yes.
It's a full screen? It's on full screen?
Yes, it is visible.
It's on full screen, right? It's a full screen slide, right?
It is not coming full screen. You have to make it full screen probably.
Full screen on my slide. Not showing full screen? No, I think it's all right.
Or maybe it is not visible in me. Let me try. Just it is full screen.
Okay, good. Okay.
So, good afternoon to all of you. And on behalf of the University Outreach Programs, I welcome all of you to this prestigious 33rd Siksha and Anusandhan Fortnightly Academic Lecture. As you know, already 32 speakers have spoken on different topics. including bureaucrats, ambassadors, professionals, academicians. So today we are privileged to have amongst us the Senior Professor of Institute of Physics, Bhubaneswar, Professor Dr. Ajit Mohan Srivastava. Welcome you, sir. And today's topic is also very, very interesting, and black holes. So the audience actually consists of honor students, faculties, general audience also. So sir can come down to your level in explaining the physics behind black holes. So I have the privilege of introducing him to all of you. His present position is professor in the Institute of Physics, Bhubaneswar. He completed his BSc in 1981 from Allahabad University and did his master's in 1983 from Indian Institute of Technology, Kanpur. Then he had his PhD in 1989 in theoretical high energy physics from Syracuse University, Syracuse, New York, United States of America. From 1989 to 92, he was research associate in Theoretical Physics Institute, University of Minnesota, Minneapolis, Minnesota, USA. From 1992 to 94, he was research associate Institute for Theoretical Physics, University of California, Santa Barbara, California, United States of America. And he is faculty in this Institute of Physics, Bhubaneswar, since 1994. His area of research is elementary particle physics, cosmology, evolution of the universe, quark-gluon plasma, topological defects, liquid crystal experiments. Actually, this is just a professional introduction of Professor Srivastava, but he is very, very, the popularization of science is very close to his heart. He is associated with many such activities, along with the Patani Samanta Planetarium. And I have the privilege of sharing the dais with him in one or two events. So I request you, sir, to kindly, we are really privileged to have you. And I will also request, as you know, because the university will bring out a commemorative volume. This is the second series of the SOAFAL lectures. The first book is under editing, and the second book is also after the completion of the second series of 25 lectures. We will be bringing out another volume. So I will request you to kindly share the write-up of this talk after the at your leisure time. So I request you on behalf of the audience, on behalf of the university, I extend my warm welcome to all of you, and specifically the speaker. Now, sir.
Thank you, Professor Sharma. It is indeed a privilege for me to be able to address the audience on this occasion. Yes, you are absolutely right. Outreach is very close to my heart, and this is a great opportunity to be able to talk to general audience on a topic as fascinating as black holes. Black holes are, of course, they have been of general curiosity and interest always. Whenever I give a popular science talk on anything relating to the universe, the most often asked question is about black holes. But of course, black holes have become of even more general curiosity and of interest since the Nobel Prize in 2020. It's interesting, this Nobel Prize given in 2020 on black holes is two parts. One is observational and one is theoretical. And observational part is generally people can appreciate. It's a beautiful pictures you must have seen. I will also share those pictures of black hole. People have also seen in movies like Terror. But the mathematical work, extremely advanced mathematical work by Roger Penrose, built up on many works by other people. I'll mention that, including Professor Raichaudhuri from India and Stephen Hawking also contributed in that direction. So these are very mathematical works, but they lay at the foundation of the concept of a black hole and the fact the black hole is a real object out there. And so this has brought this work of extreme mathematical complexity to a common person. That's nice. And I'll say a few words about this and try to explain to you some of those aspects. So Let's start with the simplest thing. So what is a black hole? And what I will try to do is, as I understand, I have a general audience, students also there. So I will not use equations at all, except one or two very, very simple equations which people study at 9th, 10th level. So other than that, no equations. So let's start with the common experience. We are our family, you throw a stone up, it goes up and it falls back. I throw harder, it goes much higher, and then again it falls back. Now, very, very hard, if you throw, very high velocity, it's natural to ask question, can I throw it with a sufficiently large velocity that it simply doesn't come back on Earth? And yes, there is a velocity like that. It's called escape velocity, natural term. If you throw a stone, neglecting air resistance, if you throw a stone with that kind of velocity, it will simply not come back on Earth. It will just fly away from us forever. The velocity of that is extremely large, 11.2 kilometers per second. Nothing can be thrown with that velocity, except some experimental things they are having. So it requires 40,000 kilometers per hour speed. This is the speed at which spaceships travel out in empty space. So that is the escape velocity on Earth. Of course, the value of this is tied up with how much gravity we feel on Earth. So if gravity, so this is the pictorial representation of that. This is say Earth, and you throw a stone with a small velocity, it falls back. Larger velocity, it goes up and still falls back. If you throw a very, very large velocity, it will simply fly away. And that velocity above which it flies away is called escape velocity. Now, so let's start discussing now. If Earth was much heavier, but had same size, but much heavier, so that means density is larger, gravity will be stronger. It will be harder to throw things up. Of course, we all will weigh heavy. We'll be very heavy also, but it will be harder to throw things up. And escape velocity would be larger. So it's natural to ask, we all know that, I suppose that the largest speed we know of any object is light. There's nothing we know which travels faster than the speed of light, faster than light. And the light speed is 300,000 kilometers per second. It goes almost 1 second from here to the moon and comes back in another second. So it's natural to ask that, if suppose Earth was so heavy that the escape velocity became larger than the speed of light, what will happen? The light will also not be able to escape. And since nothing we know travels faster than light, nothing will escape. And that is the concept of black hole. Earth would then become a black hole. So in simple terms, if Earth was same radius but sufficiently heavy that the escape velocity becomes larger than the speed of light, then nothing can escape from Earth. That would be Earth would become a black hole. For that, Earth will have to become 2 billion times heavier. 2 billion times heavier. So this is what it is. So Earth of same size and dark shaded means heavier, heavier, heavier. So stone, of course, travels shorter distances, but even light, this person is holding a flashlight. Even light doesn't escape from black hole then. It just falls back on black hole. Now, there's one way of increasing force of gravity is to make Earth heavier. Another would be to take the same, in that case, you have to increase the mass. I said okay. So the Earth will have to become heavier than 2 billion times than its mass. But suppose you don't change the mass, you still want to change the gravitational force. What you have to do, you have to compress the Earth. Because the force of gravity depends on the mass and also the distance from center. So if you compress the Earth, then gravity force will increase and escape velocity will increase. So one can ask the question again, how much I have to compress the Earth such that the escape velocity on the surface of the Earth becomes larger than the speed of light. Earth has presently radius of 6,400 kilometers. That's the radius. And if you do calculation, you will have to compress it to a size of 1 centimeter. This is amazing. 6,400 kilometers is the size radius of the Earth right now. You have to compress it to size of 1 centimeter. Then escape velocity on its surface will become larger than the speed of light. Earth would become a black hole. So that's the pictorial thing I have written. This is the Earth denoted radius 6,400 kilometers, escape velocity presently 11.2 kilometers per second. Compress it. So that's 1 centimeter dot I have made. Compress the whole Earth down to size of 1 centimeter, then nothing will escape from that. Escape velocity will become 300,000 kilometers per second. Even light won't escape, so nothing will escape. Earth would be a tiny black hole of 1 centimeter size. But imagine same mass. Okay. So black holes are extremely compact objects. The sun, which is 1,000,000 times heavier than Earth, if you compress sun sufficiently, it will also become black hole. So one can ask the question, how much you have to compress it? Yet the size of sun is 1,000,000 kilometers. At present, size of sun is 1,000,000 kilometers. You have to compress it to a size of 3 kilometers. When the sun is compressed to the size of 3 kilometers, it also can become a black hole. So here I have a couple of equations, and this is so general people can neglect it if you're not familiar with the equations, but I think it will be useful for students because they're such trivial calculations is useful. We know that this is taught at 9th, 10th level. Gravitational attractive potential energy of a body of mass little m at the surface of a large body of mass m. Suppose Earth. So this is Earth, radius r, its mass is m. You keep a tiny stone of little mass m. What is the gravitational binding energy? It is minus capital G m mass of Earth times little mass of the body divided by radius of the Earth. G is the gravitational constant, Newton's gravitational constant. Minus sign is very important. It denotes attractive force. That is the gravitational binding energy. This is the energy by which the things are held to Earth. If you throw the body up, it develops kinetic energy. Kinetic energy is half mv square. So what do you expect? You expect the body should become free. It should not be able to remain bound to the Earth if kinetic energy becomes larger than the potential energy. If energy of motion is more than what is holding it up. So half mv square bigger than gmm by r, magnitude. Sign means it's attractive, so you have to become bigger than magnitude. You just simply solve this equation, the little gets cancelled, and velocity is square root of 2 gm by r. G is gravitational constant, mass m is mass of Earth divided by r. So this is the velocity. So actually, if you put radius of Earth right now, so this is the velocity I have given. Escape velocity from surface of a body of mass capital M, radius r is 2 gm by r. If you put mass of Earth here, put radius of Earth 6,400 kilometers and G gravitational constant. I have not given value, but you can check. You simply do this calculation, square root 2 gm by r. Surface of Earth, velocity will come out to be 11.2 kilometers per second, which is I told you. 40,000 kilometers an hour. Actually, it's the interesting thing to know that black holes have been observed somewhat indirectly, but the object we have been able to observe more directly, with the highest density in the entire universe, is called neutron star. I'll say a few words about how neutron stars are formed. So neutron star is the most compact object. Its density is 10 per 14 grams per centimeter cube. It's like taking a whole mountain and compressing in the size of a tiny ball. That's the dense. These objects, we know, we study them. So that which should have an incredibly large escape velocity, and indeed it is. It is about 2 times 10 power 8 meters per second. This is about 60% of the speed of light. So almost speed of light, but light can escape from neutron star. It bends, but it can escape. So with this thing, we can actually make calculation now. So this is the velocity, escape velocity from a body of mass m and radius r. And what we said, you get a black hole, if nothing can escape velocity becomes speed of light. So just put c here, v equal to c, and it will tell you what should be the mass and radius. So you simply put v equal to c in this equation. But this actually, this is very interesting. This question was asked long before theory of relativity or anything. Because people knew gravity force and people knew that speed of light is very large. So Pierre Laplace asked this question then. What would happen if escape velocity was larger than speed of light? So you put v equal to c and you simply say 2 gm by r square root is equal to c. So this gives you radius is equal to 2 gm by c square. This is the speed of light. This is interesting. So that if a body of mass m has this radius, escape velocity becomes larger than the speed of light. So it will become a black hole. This calculation I have done, you notice, is using Newton's equation. But Newton's law of gravitation doesn't hold for very strong gravity. What we need is, and I'll have a few slides on that, Einstein's general theory of relativity. It modifies Newton's laws. But interestingly, the modification is such that this formula still holds. You know, sometimes what happens is you'd have two different kind of mistakes and they cancel each other. That's what happens in this case. This formula still holds correct. So even if you do full calculation from Einstein theory, this is the correct formula. That if you have a body of mass m, then if its radius is this given by 2 gm by c square, it becomes a black hole. This R is a very important number. This is called Schwarzschild radius. Schwarzschild was the scientist who first calculated this, and also called event horizon. It's called event horizon. It's a kind of horizon. Nothing goes beyond this. Everything is trapped inside it. You can't see beyond it. So horizon means something you can't see beyond it. No? So there's nothing escapes from this. So the size of event horizon of black hole, I have denoted RBH, is 2 gm by c square. So here I have given, if you calculate event horizon size for different objects like Earth, Jupiter, and Sun, this is given. So the mass is given. Once mass is given, you simply put the mass here. G is gravitational constant. Its value is given. You can just take from internet. And C is speed of light. Simply put that mass. You can calculate yourself value of R. So for Earth, I told you it will be 1 centimeter. Jupiter it will be 3 meters, and Sun will be 3 kilometers. But remember, to become a black hole, these objects need to be compressed to this size. Earth needs to be compressed to 1 centimeter. Jupiter needs to be compressed to 3 meters, and Sun compressed. And it cannot be done. There is no physical process by which you can do this thing. A sun will never become a black hole. But it turns out that very heavy stars, they eventually automatically get compressed to small sizes because of gravitational attraction. I'll say a few words how black holes are formed, and they become into black holes. The important thing is, I said that if you compress it to that size, so it looks as if a black hole is a extremely compressed solid object. It is not actually. Black hole is not like a solid body. So I will say how it forms. Black hole forms after complete gravitational collapse of massive body. So I'll tell you how it forms. For example, a very heavy star. Star is balanced because there's a lot of energy being produced in center, so it's trying to collapse by gravitational force, but there is a radiation being produced in center, so it balances it. But eventually the radiation dies out, star dies, and it collapses. When it collapses down to a point. Black hole is formed when nothing can prevent a collapse, gravitational collapse. And when it collapses, gravity wins, and gravity wins all the way through. So it collapses down to a point, but its mass remains the same. So mass, which is a million times heavier than, say, Sun, million times heavier than Earth, if it collapses, our Sun will not collapse, but a star 10 times heavier than our Sun would collapse. So 10 million times heavier than our Earth, it collapses, it retains the same mass, but its size becomes zero almost zero. So the density, that means at that point becomes almost infinity. Mass is 10 times, million times heavier than Earth, and size is almost zero, so density becomes almost infinite. So, but if its size is almost zero, what is the size I'm talking about? I'm saying the black hole has this size. This is the size of region around that central, extremely dense singularity from which light cannot escape. Anywhere inside that region, the escape velocity is larger than the speed of light. Outside that size, you can escape. That boundary of that region is called event horizon. So here I have given examples. You take a star, ordinary star, and there is a light rays. I have denoted light rays. They go pretty straight. They do bend little bit by force of gravity, but that bending is so little on a star, I can't draw it in this picture. Our sun will become a white dwarf. It has a million kilometer size right now, but it will collapse down to eventually size of few thousand kilometers. And its gravity will become a lot stronger. And light will slightly bend going out from this. Because of force of gravity, light will bend. Neutron star, I told you escape velocity is 60% of the speed of light. Light bends very strongly, but still it gives out of the star. Now you see, all these I have denoted as blue objects because these are actually compact, dense objects. These are solid objects. Solid or gaseous, whatever, but they are objects. Black hole, I have not gone anything blue. It's empty, but I have denoted a singularity here. And I have denoted a dashed circle here. It's dashed circle because there's nothing inside this dashed circle. Nothing. All the mass, the star collapsed to black hole, all mass has gone to the center in the singularity. But the gravity is so strong in this all empty region. This empty region, entire empty region, the gravity is so strong that if you were inside this shaded region, dashed region, nothing can escape. Light cannot escape. But outside this, light can see. Light has bent. It goes out and bends back here. But if you're a little outside here, light can escape. This region is called the horizon, event horizon. So this is the important point. A black hole is nothing but an empty region. In the center, there is a singularity which is all empty space, and the region inside which everything is trapped is called event horizon. And this is the notion which Roger Penrose had given, something related to trapped surfaces. It's related, event horizon related to trapped surface. This is the region inside which everything is trapped. So it starts with very natural, no? Trapped. So theorems about the singularity, so Roger Penrose actually showed that if a star collapses down to this size, this is the Schwarzschild radius or the event horizon. If it collapses down to this size, up to this size, no problem. You can maintain the size, neutron star or something. But once you collapse to this size, nothing can prevent the further collapse. It will collapse down to singularity. So Roger Penrose gave theorems that singularity will necessarily form once the object collapses down to that size, and that's the Nobel Prize given to Roger Penrose. Now, to understand the black holes with very strong gravity, we need theory of gravity. And our view of gravity has changed. The Newton's theory will not work simply. Newton's theory of gravity, in which everything was fixed flat space-time. When I say flat space-time, what I mean is, when we teach Newton's law, you draw on blackboard XY coordinate, you throw stone up, it draws a parabola, it forms a parabola. And you calculate writing questions on X and Y. And the bodies attract each other by gravitational force. But Newtonian gravity is not valid for very strong gravity, or when velocity becomes close to the speed of light. So you need to modify it. So Einstein did that modification. He changed Newton's theory. But this change was so dramatic. He didn't just say that Newton's law of force, which is J m to be r square, you have to make some modification. He changed the entire picture of gravity. He said, no, when we write down the coordinates on blackboard, XY coordinate, XYZ coordinate, this is not correct. You cannot write down this kind of coordinates, because when there is a massive body, the space around it cannot be described by XYZ coordinates like that. It's not Cartesian coordinates won't work. Cartesian coordinates don't work. Why they don't work? You see, if you see a globe of Earth, you don't write down XYZ coordinates. What you have longitude and latitude. Why do you have longitude, latitude? Because the angles, because it's a sphere. So curved surfaces cannot be described by Cartesian coordinates. So Einstein said that when there is a massive body, space becomes curved, something like a curved surface. And the effect of curvature of space manifests itself as force of gravity. So gravity is not a force, it's just a manifestation of curvature of space-time. So this is actually a very beautiful concept. It's complicated, but it can be explained in simple terms. That's what I'll try to explain to you by using an analogy. So in Einstein's theory of gravity, there is no such thing as gravitational force. What appears to us as attractive force is due to motion of bodies in a curved space-time. What's the meaning of curved space-time? So let's start with a very simple picture. Let's imagine there is a rubber sheet. Let me just start with it. This is Earth, and there's some kind of rubber sheet I have drawn here, mesh here, which is bent. It has a deformation inside it. That's what it means. You could have a flat mesh, or you could have a deformed. Deformed thing is curved. When it's not deformed, it's flat. It's flat. As simple as that. Now, Earth causes deformation. So how does it produce force of gravity? So let's imagine this. Suppose you can do this, I think. Suppose you are in a lab. You make a transparent rubber sheet. Transparent. Use the transparent rubber sheet and put a heavy ball inside on the top of it, metal ball. What will happen? It will deform the thing naturally. It will deform it. Now put a little marble. This number 1 red, I think, is the marble. What will happen? It will roll towards it. You see, this is rubber sheet, and there's a heavy body. It causes deformation. You put a little ball marble up there, it will roll towards it naturally. Now suppose your friend walks inside in your lab and sees this happening. Your friend does not know that you have made a transparent rubber sheet. Your friend does not see rubber sheet at all. What the person will see? That person will see there is a massive body and there is a tiny body rolling towards massive body. That person will say, oh, wait a minute, this heavy body is attracting this body by some force. That's what the person will say. This is exactly what when you take a stone and drop it, a stone falls towards Earth. It falls below because there is a force of gravity. But here you see that there is no force here. It is rolling down here because of the curvature. If you draw a little bit push here, it will move towards in this direction. So in flat sheet, it doesn't happen. Of course, on a flat sheet, it will not happen. On a flat sheet, it will not happen unless it is pushed that way. Now, one thing is tricky. In this case, actually, I'm using force of gravity. You see, in some sense, because it is moving because this deformation is caused because of force of gravity. So it's an analogy. It's an analogy. What I'm trying to say is, suppose this sheet was flat and the ball was not there. In your lab, you put a body here and leave it. It would not go anywhere. It will remain there even though force of gravity is there. But when this body causes curvature, then this moves there. Let's take another example. So I told you that again this deformation caused by the heavy ball and rubber sheet, this rolls towards it. So suppose you take another ball and throw it with some velocity in tangential direction. What would happen? It will go in circles. This is something you would have seen in exhibitions. Sometimes there is something I know it's called Maut Ka Kuan. I don't know if you have seen it in exhibition. There is a well, there is a ball kind of well, and somebody with a motorcycle will go like that in that. It goes in circles in that. There's no. Why does it go in circle? There's no force pulling it. You know that for a body to go in circular motion, there must be a centripetal force. Something must have studied in physics. Something needs to be pulled. Earth goes around sun because there is force of gravity. Moon goes around Earth because force of gravity pulling it. But when you see a person with motorcycle going in circle, why is it going in circle? There is no force in the center. It's going because the surface on which it's moving is curved. It's like a ball. So here same thing will happen. If you take this rubber deformed surface and you throw a ball with right velocity, it starts moving in circles, which is exactly like moon going around Earth. If the velocity is very large, you throw something, it will bend, but it will fly away. This is like comets. Comets go around sun and they fly away. Or sometimes comets come around Earth, don't fall on Earth and they fly away. You see, all this is exactly the behavior of gravitational force. Gravity behaves exactly in this manner, but all these features have been produced not by assuming any force here. It's simply happening because of the curvature of this surface, the deformation in the surface. So this is basically the essence of Einstein's theory, that the force of gravity is manifestation of the curvature of space-time, and actually there is no force. This is exactly the force. So this is sun. Earth goes around sun not because there is a force of gravity attracting Earth towards sun. There is a deformation. This mesh denotes, it's a symbolic thing. There is no mesh out there. It's a space. If you do calculation, space will behave. So actually the equations of curved space behave exactly like I have told you. It's the equations on a rubber sheet. Exactly like that actually. So if you do motion of Earth around sun with the curved space, it will start going around circles with some velocity without assuming any force. Satellite going around Earth. And by the way, I have shown dimple caused by sun and also tiny dimple caused by Earth. Earth is also heavy, you know. Satellite goes around Earth because Earth causes a dimple in space. Satellite also causes a dimple. Satellite also has a mass. Everything which has a mass causes a dimple. But satellites are very tiny, very little mass. So that deformation cannot be shown in this picture. So I showed you this picture earlier. The strength of gravity is different around different astrophysical objects: star, white dwarf, neutron star, and black hole. Force of gravity becomes stronger. But these are pictures I showed you like a solid body, and the force of gravity was manifested as the force of attraction. But now we say that okay, force of gravity should be manifested in terms of curved space-time. So how does curvature look around these objects? This is the picture. This is the curvature of space around this Earth, rubber sheet. Sun has a much stronger gravitational force than Earth. So you see it's much more deeply curved surface here, much more deeply. Our sun eventually will get so much compressed, it will become white dwarf. This deformation will become much deeper. And what happens for a black hole? This deformation becomes so sharp, it's called as a puncture in a space-time. It's not really puncture, but it becomes singular. And it goes down very, very sharply in deep. This curvature becomes very sharp. So this curvature, how much curved the body is, contains the notion of how strong the gravity is. When you actually see the pictures people say of black hole collisions and all that, they sometimes give in terms of the curvature of a space-time. So now a very interesting thing is that we say that heavy bodies curve space. So this is the dimple. Now, if Earth moves, the dimple will also move. The dimple is at the place where Earth is. So if Earth moves, the dimple moves. Earth goes around sun, dimple moves around the sun, like that. So if the body oscillates, the dimple will oscillate. So it's like that if you take a water surface and you throw stone, that these oscillations are produced, they travel like waves. Same thing will happen if some body, massive body oscillates. They oscillate. Sometimes they have two stars going around each other. So the motion of the two stars going around each other produces these oscillations. And these oscillations in space curvature travel like a wave. This is called gravitational wave. This gravitational wave was a prediction of Einstein's equation. Einstein made this prediction, and you must have heard gravitational waves have been observed about 4 or 5 years ago. So this gravitational wave observation, which was, and these gravitational waves travel. So this is just like actually you throw a stone in water pond and the waves travel, but the waves travel there in water. But for black holes, you don't need any medium. They're like light. Light travels through vacuum. From stars to us, there's no medium in between. Same thing, gravitational waves. They just travel in empty space. So the important difference between gravitational waves and electromagnetic waves, like light, etc., is the gravity is an incredibly weak force. You see, the electric forces and magnetic forces are very strong. You see, you take a magnet, and you can use a magnet and take an iron pin, paper clip, and it will get pulled up by the magnet. The paper clip is being pulled down by the whole Earth. Earth tries to pull down this paper clip, but a tiny little magnet is able to pull it up. So the magnetic force of the tiny magnet balances the force of entire Earth. So it tells you that gravity is very weak and magnetic force and electric forces are very strong. That's why producing and detection of electromagnetic waves is very easy. You take tiny mobile, it produces signals. You send signal to some, you send your message somewhere else, you talk, and it's also able to receive signals. So detectors and transmitters of electromagnetic waves are very easy to make with tiny. But gravitational waves can only be produced by extremely massive astrophysical objects. And to detect them, you need very sophisticated detectors. It was the LIGO, Laser Interferometric Gravitational Observatory. You may have heard about that. I don't have time to talk about that, but this is an observatory which is about 4 kilometers in size. A detector 4 kilometers in size that is able to detect these gravitational waves. This was detected on September 14, 2015, was the first detection, and a Nobel Prize was given for that also. LIGO observed gravitational wave. An interesting thing, which why it's related to our talk, this talk is the first detection was from a merger of two black holes. Two black holes collided. This was the most direct observation of a black hole yet. Two black holes, about 30 times mass of our sun, heavier than that, and about 1 billion light years away. They were going around each other, like Earth goes around sun, but they collided, and they emitted huge amount of energy in gravitational waves. Black holes, I told you, are empty space. So this is empty space colliding, but it's 4 regions of strong gravity. It collided with each other and produces incredibly large amount of energy. The energy released was so much. I have done a calculation. Ignore the top thing here. Only notice the following thing. Okay, let me just not show this slide. I will get confused. The energy released by those black holes at that time was so much that gravitational wave energy contained at that time, the wave came only for a few milliseconds. During that time, that energy was larger than the energy of all the stars in the entire universe, what we see. There are about billion stars in a galaxy and about 1 billion galaxies. So huge amount of stars in our galaxy, but all the stars together were producing light. And this black hole, let me just skip that part. So let's just remain here. So this energy which was produced by the black hole collisions, it was in gravitational waves, and we were able to see it using LIGO detector. If we did not have LIGO detectors, we'd never have known that two black holes have collided, so much energy has been produced, because they don't emit any other signal. So there are a lot of black holes in the universe, we know by now. So many black holes are about, these black holes were 30 times heavier than our sun, so tens of times of our sun. But then they are supermassive black holes. The masses of those black holes are million times and several billion times larger than mass of our sun. These supermassive black holes occur in centers of galaxies. Now, galaxy consists of billions of stars, And our sun is in one such galaxy, which is Milky Way. Our own galaxy is called Milky Way. And there is a supermassive black hole at its center. So this is not our galaxy. We cannot picture our own galaxy. If it was, but this galaxy is pretty similar to our galaxy. Our galaxy is a spiral galaxy. This galaxy is called M83. But our galaxy, if it was our galaxy, the sun would have been somewhere in spiral arms. Our sun is in Milky Way in one of the spiral arms. And it is not in center. We are very happy it's not in center because in center there is a supermassive black hole. The size of a galaxy is about 100,000 light years. Light years is the distance people use in astronomy. Is the distance light travels in 1 year. It's about 10 trillion kilometers. So the solar system, if this was our galaxy, would be one of the spiral arms, and the center there is a supermassive black hole, which is about 4 million times heavier than our sun. How people know that? How do we know that? So this was the incredible set of observation. This is Gage and Genzel, the remaining two of the Penrose got for theoretical work, and these people got the first prize for observation. This is image from European Southern Laboratory shows they were able to see the two different kind of pictures. One picture I'll show you is a picture of accretion disk, but this is they were able to track the stars going around the sun, around the central object. So in the center of a galaxy, there's a lot of dust. So this dust, because of dust, you can't see this region directly. But they were able to, by using sophisticated telescopes, they were able to track down the stars moving around it. And what happens is that if you know the orbit of an object, you can find out what it is orbiting about. For example, if I know the velocity of the Jupiter goes around Sun, if I know the velocity of Jupiter at a given point and distance of Jupiter from Sun, I can calculate mass of Sun from that. This is calculated from Kepler's laws. Newton, applying simply Newton's laws. Newton's laws for such distances, such weak gravity can be used. But you can, of course, modify it by Einstein's equation, and then you can do this calculation. So they were able to track the orbits of these stars, and these orbits of these stars around the central object, where they tracked, and they knew the orbit, its size, and they knew the velocity. From that, they calculated the mass, and they found the mass is about 4 million times the mass. This is how they detected this black hole, central black hole. Another set of detection, this is by Event Horizon Telescope, you may have seen. This is right-hand side picture is picture from our own galaxy. The left side picture is from a different galaxy, M87. M87 has a black hole which is 2,000 times larger than the mass in our own galaxy. In our own galaxy, the black hole is at the center of the galaxy, and that center of the galaxy falls in a constellation. We know we have different constellations in stars. There is a constellation called Sagittarius. We don't see it. We are in northern hemisphere. Southern hemisphere, people can see this constellation. It is in that constellation, the center of galaxy, our galaxy. And that is where, so it is actually called Sagittarius A star, it's called that black hole. People are able to, making radio telescopes, they're able to observe this kind of bright rings. These bright rings occur when gases are absorbed by black holes. And these pictures are observed because the light coming from this ring, when it reaches you, is bent by the force of gravity. So I'll say a few words later about this. So this is what it is. This is, if you see as a diagram of this thing, if this is a Milky Way spiral galaxy, center would be Sagittarius A star, this Sagittarius constellation here, and solar system would be somewhere spiral arm, and this will be about 26,000 light years away from you. So how does black hole form? How do black holes form? Black holes form from gravitational collapse of a star. How does a star form? So originally there was no sun and no planet. There was a gas cloud, and gas cloud condensed. It condensed, the central part became very hot and dense, and density and temperature became so large that nuclear reaction started. Nuclear reaction, the diffusion reaction, this is a hydrogen bomb, you may have heard about hydrogen bomb, in which deuterium is fused to heavier element, helium. So these nuclear reactions take place. They have been taking place in our sun. So when the density is sufficiently large and temperature is large, then hydrogen and deuterium nucleus are able to fuse to heavier element, and they release this is called nuclear reaction. The final mass of the helium is less than the mass of the nuclei which fuse to form it. So where the rest of the mass goes, E equal to mc square, Einstein's equation, goes into energy. That's the nuclear reaction. And collapse of the star is then halted as pressure equilibrium achieved. What happens is the star is trying to collapse. Gravitational collapse compresses the star, density becomes large, temperature becomes large, nuclear reaction starts. Nuclear reaction starts, too much energy is getting produced. That radiation pushes out the gas. So it's not able to collapse further. So our star, sun, is in equilibrium right now. The center is trying to expand it and gravitation is trying to collapse it. They are in equilibrium. So eventually, hydrogen will finish, helium will finish. Hydrogen will finish, deuterium will finish, helium will remain. Helium will have to fuse. Helium will fuse to other elements like carbon. Then carbon can fuse to other elements. And this is how successive elements are formed. Final element which is formed in such reaction is nickel and iron. Iron cannot be fused further because it's not possible. Iron nuclei, when you fuse, they don't give any energy. That's a dead end. So once the iron is produced, star dies. Our sun will not even be able to produce iron. Our sun is not very heavy. So it will produce helium. It will produce helium. Then after helium, it will produce carbon and oxygen. But carbon, oxygen, nuclei, they have a lot of positive charge. To fuse them, you need to overcome that positive charge repulsion force. It's not possible. It will not have sufficient density and temperature to fuse. So it will reach a stage when its core is consists of oxygen and carbon until it stabilizes there. It will stabilize by quantum forces of electrons actually. Let's not worry about that. That number was given by Chandrasekhar. What will be the size of this object? What will be the mass of this object, maximum mass? It's called white dwarf. So our sun will become white dwarf. But what happens is the star is much heavier than our sun. If a star is much heavier than our sun, then it can form up to iron. And iron, after that, iron, nothing can fuse further. Iron core collapses. It collapses, its central part of iron becomes a very dense object, which extremely large density, and outer part bounces in a shock wave. That's called supernova explosion. And central object can become a neutron star, I told you about. But if the collapsing core is very heavy, 2 to 3 times mass of sun, then even neutron star is not formed. Neutron star, what happens is very dense because when the gravitational collapse gets balanced by the quantum forces of neutrons. But even quantum forces of neutrons have a limit. Once the star is heavier than that, gravitational force becomes so strong that even the neutron quantum forces are not able to balance it, then complete collapse. So what happens in that case is the star is able to collapse down to a size which is less than its Schwarzschild radius, event horizon size. The moment it goes below that size, I told you there are singularity theorems by Penrose and all these people. Then nothing can stop it. You don't have to worry about it. Nothing can stop it after that. So this is the picture that white dwarf is formed when the quantum behavior of electron balances the gravitational force. Neutron star is formed when the quantum behavior of neutrons is balanced with gravitational force. Black hole is the final victory of thermodynamics. Okay. And I will talk this about later. Evaporation of black hole, I talk about it. So important thing is black hole formation inevitable? This is the Nobel Prize given to Roger Penrose. Answer of this question also shows the most important difference between Newtonian concept of black hole and the modern concept of black hole, with general theory of relativity. I told you, even with Newton's gravity, you could think about a black hole. How then, what should be the escape velocity such that even light can't escape? That's a Newtonian calculation. You can do it. You get the right answer. But you can always say that in Newtonian gravity, you can always imagine that there will be some force which will balance the gravitational collapse. Pressure balances. Gas pressure or some kind of pressure will balance the gravitational force. So if gravitational force is trying to compress it, and there will be some kind of pressure. We don't know all forces right now. We know to some physics. You know that there may be some kind of force which will balance it. This is what is the importance of general theory of relativity and the work of Penrose. You can rigorously prove that under some situation, singularity inevitably forms. This is important thing is that the foundation was laid down by the work of Rai Chaudhary, A.K. Rai Chaudhary. He actually calculated the motion of object under falling under force of gravity, and he gave certain equation. It's called a Rai Chaudhary equation actually, and a very famous equation. And using the Rai Chaudhary equation, Roger Penrose and later Hawking also did some work on that. Roger Penrose showed that don't worry about what I've written here. That if the mass of a body is contained within a radius r equal to 2g, this is the Schwarzschild radius, event horizon. If the body mass is contained within that region, then nothing can stop complete gravitational collapse. It will collapse down to singularity. Even if there is unknown forces, how can you make that kind of statement? Even if we don't know, you can always take it. Suppose there is a force sufficiently strong, which is a repulsive force, it will balance it. What happens is, in Einstein theory, pressure also contributes to attractive force of gravity. Pressure, so it's interesting. So the star is trying to collapse, like sun. There is a radiation pressure. Radiation pressure is balancing it. Repulsive force, no, it's trying to balance it. It's repelling the collapse. But actually, this pressure is also adding a little bit to attraction, gravitational attraction. In sun, it is two very tiny effects, but can become very strong. So let me tell you what happens is, this is the Newton's law of force, gmm by r square. If you make a modification of that using Einstein's equation, they get modified by that. Force is proportional to the mass. This is density I have written simply, but this is a pressure component. This is a pressure component. It will be the modification of Newton's law for the gravity. Actually, you should not be thinking of force, I told you. You should think about curved space. But what happens is that you can take approximate calculation. You say, okay, there is a curved space, but I want to do approximate calculation as if there is a force of gravity by Newton's law. But then you have to change Newton's law. And the change is the following. Apart from mass, so apart from the mass here, you'll have to introduce some component which is pressure. So pressure actually adds to the force of gravity. So pressure does two jobs. In our sun also, pressure is trying to balance it also, stop gravity, but also adding little bit to this. But only problem is adds by divided by c square. So in sun, it is not divided by c square makes this effect very small for object like sun. But for object like when you compress it down to size of a event horizon, this factor becomes very important. So after that, whatever pressure you put, it doesn't matter. So even unknown forces will not be able to stop. This is the singularity theorem, Roger-Penrose singularity theorem with trapped surfaces. The trapped surface will form. Everything will be trapped inside that intuitively. So how to detect a black hole in the universe and not even light comes out? I showed you those bright pictures, bright images. What happens is the black holes typically have gases around them or some other object. So the gas falls. Nothing comes from black hole. But when gases enter into black hole, they get very compressed. And they get very compressed, they become very hot. So they emit light or radiation. That radiation detected. That's how you detect. So this is a picture, for example. This is a black hole, tiny black hole somewhere there. A star, neighboring star, gas is pulled inside and goes around and gets absorbed by the black hole. And the black hole compresses the gas so much because black hole is very tiny in size, it gas becomes very hot, emits jets. Those jets have been detected. This is the indirect picture of indirect evidence of a black hole. And this is also, this is called accretion disk. This is the picture I showed you earlier. This is the gas being absorbed by the central black hole of our galaxy and other galaxy. And this is this bright ring is that of it's called accretion disk, gas getting absorbed by the black hole. Important part in this case is some part of this actually image is behind the black hole. There is a black hole behind the black hole, but light coming from black hole bends around the black hole and reaches us. These pictures are beautifully shown in a picture called Interstellar. If you ever see the Interstellar movie, there's a beautiful picture of this kind of accretion disk there. So last topic, which I'll just take 5 more minutes. Is that okay, Professor Sharma?
Yes, sir.
So this is 5 minutes. So do black holes live forever? Because they keep absorbing everything. Nothing comes out of that. You would think black hole lives forever. But that's not true. Black hole actually emit something called Hawking radiation. This is a quantum effect. So this is, let's see, I'm showing you. When I told you that escape velocity larger than speed of light, that's all classical, But there are quantum things happening. Quantum things are very funny. Quantum mechanics tells you that some things can happen which you don't expect from classical mechanics. For example, there's a vacuum, there's nothing, no energy. If there's a photon coming, photon can produce particle-antiparticle pair. But in vacuum also, sometimes electron-positron pairs can be produced and they can annihilate each other. So energy can fluctuate for very tiny time. Energy is conserved generally, but can fluctuate for very tiny. It's called uncertainty principle. So what happens is, this is the event horizon of the black hole. I have drawn here roughly. There's nothing inside. So don't get confused. The blue is a solid thing, nothing. It's an empty region. I should have actually drawn a dotted picture, but this came from internet. So this is nothing here, but there's a dotted line here which shows the event horizon Near that, particle pairs can be produced by quantum effect. But normally what happens, they get produced and they annihilate each other again, and you don't see it, what's happening. But what happens is, they can be produced in such a manner that one of the particles is produced inside the event horizon, one is outside. When you produce it inside the event horizon, something very interesting happens. So let me tell you what happens here. Particle, when they produce